So the last topic, more or less under the heading of ring theory that we'll study, is talk about three particularly interesting class of rings called Euclidean domains, principal ideal domains, and unique factorization domains. Principal ideal domains are abbreviated by the word PIDs, and unique factorization domains are abbreviated by the words UFDs. Okay. We'll start with the last two actually and get to the Euclidean domains afterwards. All these are commutative domains. So commutative rings with one where product of two elements being 0 implies one of them is 0. And here is the world of all commutative rings with 1. In there we have domains, and then these three classes are all in the world of domains. In fact, there is a strict containment. UFDs contain all PIDs. So every PID is also a UFD, and Euclidean domains are even special. Euclidean domains. So every Euclidean domain is a principal ideal domain, and every principal ideal domain is a unique factorization domain, and all these types are actually domains, and all these things are actually commutative rings with 1. And each containment here is strict, meaning there is a PID which is not a Euclidean domain, there is a unique factorization domain that is not a PID, there are plenty of domains that are not unique factorization domains, and there are commutative rings with 1 that are not domains. So that's some picture to have in mind. Okay. So recall, we have talked about PIDs a little bit already. We say that a commutative ring with 1 is a domain. Let's actually say R is a domain. Say that R is a PID if every ideal in R is principal, meaning it has the form parenthesis A for some A in R, meaning all multiples of a single element A. Okay, and we have some examples that we have seen already. The prime examples are Z and Fx, where F is a field. You can check, for example, this is an example. This is a PID. If you take all numbers of the form A plus BI, A, B, in C. This is a subring of complex numbers. These are called Gaussian integers. So these are all the points of the square lattice. Right, here is 0, here is 1, here is I. So you're taking all integer combinations of this vector and that vector, so you just get the square grid. So this is Zi. That's a PID, we'll see later. If you take Z e to the 2 pi I over 3, so cube root of unity, we'll see that's a PID. So that one is the triangular lattice. Here is 1 and here is e to the 2 pi I over 3 in the complex plane. And if you take similarly Z adjoin square root of minus 5, we can prove that this is not a PID. This is a good example to know. We'll study this in a while in detail, I think. If you want more examples, certainly, for example, if you want something that you can actually prove is not a PID, just take the 2 variable polynomial ring. This is certainly not a PID. Just show that the ideal generated by x and y is not principal. This is easy. That you don't have any polynomial that divides both x and y in the 2 variable polynomial ring. So here are some examples and non-examples of PIDs. Yeah, and we already have some nice properties also. For example, we know that every prime ideal in a PID is maximal. Yeah. So to talk about the UFDs, first I need to introduce the reducible elements. So here's the definition. Recall, this also has been given some time before, I think. A non-zero, non-unit element A in R is called irreducible if it does not have any proper factorization. Meaning what? Meaning if whenever you try to factorize it, you write it as a product of two things for U and V in R, then one of these guys have to be actually a unit. Unit, remember, means invertible in R. So of course you can take a element, any element, and write it as a unit times the inverse of the unit times A. So that's not really a factorization. So you can always pull out a unit. Like you can, if I tell you to factor 3, you cannot just tell me it's that. You just pull out a unit. That's not a real factorization in Z. Or if I want you to factorize x squared plus 2 in Qx, you cannot tell me that it is 2 times half x squared plus 1. You just pulled out a unit. So these are not proper factorizations, right? Proper factorization means into non-units. So we are saying that something is irreducible if it does not have a proper factorization in non-units, into two non-unit elements. Good. And a domain R is called an UFD if every non-zero non-unit can be written as a product of irreducible elements and this factorization is unique up to reordering of terms and up to units. It's saying that they have a irreducible factorization like we have seen in the two prime examples again, Z and Fx. See, you give me a number 30, I can factorize it, or maybe 60, 2 times 3 times 2 times 5, right? It's not unique. You can reorder. You can also write 2 times 2 times 3 times 5. You can also put some units in like this. But that's pretty much all the freedom you have. That's what this uniqueness, unique up to reordering and term and up to units mean. Yeah. And if you take fx, then you give me something x squared minus 4 in qx maybe. You can factor it x minus 2, x plus 2. Again, not really unique. You could reorder. You could also write it like this. You could also fudge with the constants, the units. So you could write 3x plus 6 and then make it 1/3 x minus 2/3. Yeah, just put a 1/3 and a 3 because those are the units in QX. But that's pretty much all the freedom you got. Yeah, so that's what the uniqueness means. So this is saying that every non-zero non-unit has a irreducible factorization, like we have seen in the 2 prime examples. I mean, we'll give more examples later. We'll see that f x1, x2, xn is also UFT. And that this one that we said, this is a good example I told you to remember, is not an UFT. It's a domain, but it's not a unifactorization domain. Basically, you can see things like this. This is a prime example of a non-unique factorization. This is an element in this ring. By the way, z at joint square root of -5 just means all numbers of this form. And you can check that this is a subring of complex numbers. So 6 is certainly an element there. You can break it as 2 times 3, but you can also break it in another way. And this is a prime example of a non-unique factorization. We'll see that later. Okay, so the first thing I want to prove is, and we'll do it in the next video, is this lemma that in a commutative domain, so we have these 2 notions now, a prime element and an irreducible element. In a commutative domain, primes are always irreducible, prime elements. This holds in any commutative domain, with 1 of course. And if you're in a PID, then the converse hold. If R is a PID, then in a PID, every irreducible is prime. We'll prove it next time, but I want to point out a corollary of this. So this ring, we know, so again F is a field, is a PID. So let Fx be a irreducible polynomial. In one variable, then this is a irreducible element in Fx. Element in Fx. The definition of irreducible element is exactly the definition of irreducible polynomial. So it's a prime element by the lemma I just stated. But then in a PID, every prime is actually maximal. So this is a prime ideal. So it's actually a maximal ideal. Since Fx is a PID. And in a PID, every prime is maximal. So if you take this and quotient out by F, the ideal unit by F is actually a field. And this would give us rather interesting fields. Take the polynomial ring in one variable and quotient out by a maximal ideal. We'll talk about this later in the next